We are back once again. It is day 73 of daily LeetCode. I'm still on my Majin Vegeta character arc, right? And yesterday we released a video called Rubius Maximus. This is a legendary spell. Once theorized that if one was able to cast it, right, then all modern day computer science problems would be solved. So we're trying to learn Ruby, right? Yesterday was pretty cool. For some reason I'm looking at coin change and this is in TypeScript. I don't know if I closed the tab where I was. No, it wasn't coin change. It was yeah, it was a different problem actually. It was called like what was the problem we did yesterday? It was something about, oh yeah, it was vertical binary tree vertical order traversal. That's what we did yesterday. So that was a pretty cool problem. We did it in Ruby. I appreciate anyone who watched the video and bared with me working through it. But I think it's a cool vehicle to try and learn some Ruby. So that's pretty cool, right? Other than that, we had some legendary comments as per usual from the usual gang, right? Thomas Wong, legendary algorist himself, mentioned an hour of LeetCode is not enough. He raises a great point, right? Because the goal is to have solved, all LC hards, right? But hopefully by going at this pace, hopefully by going slow, we'll go faster, right? And we're still on this pretty much long-term portion of reviewing older problems. I have about 40 problems reviewed right now, and I think we have about 20 remaining. Yeah, there's about 25 remaining. So that would be the goal. And it's gonna go even slightly slower now because we're doing them in Ruby. But ultimately, all of this will make sense, right, when we get where we're going. Hopefully, in retrospect, when we look backwards, right, if we imagine this as a graph and each day, right, we add another node to the graph, let's just say it's a tree, right? Every day we add another node to this tree, right? We can't go backwards, right? Because it's a directed graph, right? Hopefully, at the day, right, when we get to where we need to be going, hopefully we find a back edge, right? And we can look back where we started and say, this all made sense, right? So I think it will make sense. So I'd like to learn Ruby. There's also some things I'd like to make, right? I have some ideas. I really like to work on a couple of projects. Right now, I think that my skill level, right, the tools that I'm able to use just aren't enough, right? And I think learning Ruby is one way that we can help bridge the gap once we learn Ruby. Not to say we don't want to do the whole completionist thing, right? Because if I try to learn every single aspect of Ruby, I'll never get there. There are masters of Ruby, right, that, they're just masters, and it takes a long time to get there. I just like to get to a place where we can make sense of the code, we can write it, and I guess I'd like to get to a point where I could pretty much interchangeably solve an LC problem with Ruby or JavaScript. That would be the goal, right? And I think that would just make it simpler to read all sorts of code. And so that would be the goal there. Then we can pick up Ruby on Rails, and then we'll be able to build some more sophisticated backends, right? Right now, most of the personal projects I use most of the personal projects I work on almost always lack a database. And that's a pretty critical failing, right? Because you need to be able to save data. So most of the time I opt for on-disk storage like JSON, right? And then, there's usually some specific logic which, the data lives on the server in JSON. That single point of failure, but kind of high risk, kind of high octane, kind of spicy, kind of interesting, living on the edge there. But hopefully we can do something about that in the future. That being said, we have another legendary comment from the Copy Ninja himself. The Copy Ninja, legendary algorist in his own right, mentions W time management. I'm going to reply W human. So we need a good time management scheme, right? Right now we're looking at 30 to 45 minutes a day just because there's so many things I want to make. And it's interesting because doing these LC problems helps me reason about code. So I would just like to be able to build more things. So it kind of sucks I have to time it back a little bit, but ultimately I think it's all a good thing. Additionally, I'm thinking of making some changes to the Discord, right? I've been reading a lot about system design and just some engineering blogs from some tech companies. I was just reading one about Netflix earlier today. It was about A/B testing and how they use A/B testing to drive change that makes sense. A lot of stuff about p-values and statistical significance and true positives and confidence levels and rejection ranges, critical ranges. To be frank, 10% of it made sense, but hopefully as we keep reading, more of it will make sense. But yeah, I think it's pretty cool. So maybe I'll start posting those in Discord. Maybe we'll all have some discourse about it. We'll talk about it, see if it makes sense, maybe exchange some ideas, some cheat codes, right? Other than that, right, there's another thing I was also thinking of doing. I'm reading a book called Philosophy of Software Design right now. And I thought maybe it'd be cool if we had like a book club kind of thing. But, you know, like we said with the A/B test, maybe we'll split the Discord into two. And we'll split the Discord into two. That way, right, I'll send a message out saying, hey, we should make a book club. And then the other Discord will get no message. And then, you know, we'll test those changes and see if it's engaging. That's kind of, doesn't make sense, but it is what it is. We're going to split the HCC in half, and we're going to be picking a random member to run that part of the HCC. So you're going to want to join so that hopefully that random member who gets to lead the second half of the Hyperbolic Coding Coalition will be you. And we'll kind of have like a two-manager situation like in The Office. But yeah, I'm reading that book. And it seems pretty cool. It mentions that one of the greatest problems in computer science or software development that is untouched is the scale of problem decomposition, which is actually tangentially interesting and related to LeetCode problems, because a lot of the times what you're doing with the LeetCode problem is just decomposing the problem into maybe a problem that is already solved. For example, coin change can be decomposed into a shortest path problem, right? But I think in the book what they're trying to get at is decomposing systems, right, so that the code that we write is less complex. I don't know if anyone is interested in something like that where we'll read together, but we'll see. So I'll put the book in there and I'll just post my progress. Maybe other people will join in, maybe they won't. But either way, that could be cool. And yeah, plans for today. The plan for today is more Rubius Maximus. I think today's video is going to be called Majin Vegeta Character Arc. Once we master this, we're going to go on our Majin Vegeta. There's going to be an entire character arc where there's a lot of destruction, right? Code destruction. And then afterwards we'll be saved, right? Primarily, hopefully, through someone in the Discord battling us through code like they did in Majin Vegeta, ultimately turning me into a good character, and then we'll restore balance to the HCC. But that's pretty much a roundup of the goal for this season of the HCC. Right? So yeah, I'm gonna probably jump into, I think the problem we had yesterday was clone graph, right? I'm gonna be honest, we can barely solve this problem with JavaScript. We can barely solve this problem with JavaScript. So it honestly remains to be seen if we can solve this. We've solved it before with JavaScript, it's just our solution makes little sense. And we've been reading a lot about graphs, so hopefully we can make this make sense. But it remains to be seen if we can even solve this in Ruby. But I think ultimately it's a good litmus test or testing ground, battlegrounds, coliseum, right? Contender to hopefully get better, right? And maybe rephrase or look at the problem in a different light, right? And I think my final point is that sometimes we're doing these problems, we've already solved them before. The goal, I think, is to just see it with a new set of eyes, right? Similar to how, you know, maybe when we were younger, right? You might have walked through your high school's halls or your neighborhood, right? As a young person, right? Same thing, same routine, same old, right? But returning maybe as an adult, right? If you ever went to visit like your high school teachers, right? Or if you have to visit your old neighborhood or whatever, right? It's almost like seeing it with a new, fresh set of eyes almost illuminates a lot of things that maybe have been unsaid, maybe things we never thought about, right? So I think that's the goal, right? And then we're just looking for, I guess, some vehicle to look at problems in a new light. So that would be the goal with doing this through Ruby. But yeah, we're gonna try this with Ruby. So we shall see. But as always, make sure to join the Hyperbolic Coding Coalition /Chamber. There are thousands of people joining every single day. You're going to want to join. There are tons of cheat codes, right? Tons of tips, right? People are exchanging new ways to solve problems, and you don't want to miss out on these tips and tricks, which is actually true. So, yes, this is day 73, and we're just going to jump into clone graph. This is going to be a bloodbath or a beatdown, right? Particularly this problem is going to beat me down, but we'll see if we can figure it out. And so we'll just jump into it to start, and yeah. "45 minutes on the clock. Let's see if we can make sense of this. Given a reference of a node in a connected, undirected graph." So our graph is undirected, which means it is directed, right? If it's directed, right, and connected, a connected, directed, connected usually means that for every node, right, there's a path that exists between every other node, right? So if a graph is reachable and it's also directed, it means that, yeah, there has to be a way to visit. If a graph is directed, right, and it's connected, then I think it must have a cycle. I think it must contain cycles, because if a graph, oh no. Wait, undirected. Oh my God, I'm sorry. I don't know what I was talking about there. Undirected, right? Undirected means there's no direction, right? So that definitely means that there's a cycle. And since it's undirected and connected, right, we definitely know there's a possibility that there's going to be cycles, or actually that there definitely is. No, maybe that doesn't always mean there's a cycle, right? Because we can create a graph, A goes to B goes to C, right? Where a path exists between every node and there's no cycle. So either way, what I'm getting at is that potential cycle, right? So if there's a way for potential cycle, probably need to keep track of that. We need to return a deep copy or clone of the graph. Each node in the graph contains a value, int, and a list node of its neighbors. So we have a class, right? The node has a value, right? It has neighbors, right? You can see this declared in Ruby here. It seems like we have adder accessor. Looks like a way to declare, I guess, properties on a class. All right, we initialize value equal to 0, neighbors equal to nil, at value equals val, at neighbors equals neighbors. So maybe at is equal to this, right? And then neighbors is equal to an empty array if neighbor dot nil, right? So if neighbors is nil, then it's equal to an empty array. So we're given basically an adjacency list, right? But it's kind of like we're not really given the full graph. We kind of are. We're only given the start, right? As compared to something like an adjacency list at the start. We're pretty much given access to the starting node as input, right? We want to copy it. So I'll skip this test case format. Example 1, this is the original undirected graph. We can see that there is a cycle, 1, 2, 3, 4. This looks like a clone. The nodes are new. Graph looks the same, valid. It looks like for up here, right, you can't return the same graph, right? And the nodes were cloned. In this example, right, the nodes were cloned, but the graph is messed up. So we want to retain the values in the vertices and the edges as well. So we want a true clone. These values above and below this clone here basically serve to show us that these clones are not what we're looking for. Or they're not actually clones, right? So if that's the case, how could we clone this graph, right? At onset, we actually don't know how many nodes we have since we're given the starting node, right? So how could we clone this? I'm thinking maybe, right, what if we did something like a BFS? If we did something like a BFS, right, we could start at 1, then we'd visit 4 and 2, and then 3, right? If we did a BFS though, right, we'd be at 1 visiting 4 and 2, which means we'd know that these have edges right between 1 and 4 and 1 and 2, right? And then we'd visit 4, we visit our neighbors 1 and 2, so we could add an edge between those. And then 1, we'd visit 2, we could add an edge between 1 and 3, right? And then we'd visit 3, we could add an edge between 4 and 2, right? How would we prevent us not going in cycles? Well, we could just use discovered, right? If we haven't never discovered a node before, right? If we have 1, right? We visit, we say that we discovered 4 and 2, right? Push them onto a queue, right? And then as we visit 4, right? We don't want to add 1 onto the queue again, right? Because we've already discovered it. But maybe we want to add an edge anyway, so we can just add edges and not push them onto the queue. Maybe we do the same for 3, right? But 3 would add it onto the queue, and we'd create an edge, right? And then when we visit 2, right, we've discovered 1, right, we're not going to add it to the queue, we'll create that edge. Same thing with 3. The problem is I think we just need one way to access we need one way to be able to pretty much need a way to access our nodes during iteration, right? Because if we're at 3, right, let's say we want to create a node between 3 and 4, right? We need a way to pull 4 down, right? How can we pull 4 down? So maybe we can have something like a hash map, or maybe if we're using a BFS, I think it might have been easier if I drew this, but maybe if we're using 1, 4, right, and we want to create an edge, right, we create an edge between 1 and 4, then when we're at 4, we want to create an edge between 4 to 1, right? We need a way to say, hey, we already created 1, pull down that reference. We don't want to create a new node for 1, right? And I think that's where the problem lies. So I think we could use maybe a map to keep track of these nodes, but this would run, I think, in O of V plus E with O of V space. So let's play with that, right? Let's just say we do a BFS with hash map, right? We do a BFS with hash map, right? Let's just say our hash to start, and we're just gonna use some pseudocode to start just to verify if this even makes sense, right? And we'll say that, let's say we start with a queue, right? 1, this node, right, is in the queue to start. We pull it off, right? We can check in this hash, right, if we've ever created 1 before, and if we haven't, right, we're going to create it on the spot, which would be 1, right? And then we're now going to visit the neighbors, right, of the actual graph. It's visiting the neighbors of the actual graph, right? We're going to push 4 and 2 on, and then we can check in our clone. So this is the difference, right? This hash is going to store a node, I guess a key value pair, right, of 1. Let's just say, right, to a reference to this node that actually has 1, right? But what's important to note about this hash is it's not going to store the nodes that already exist, right? We don't want to do this, right? We don't want to return the same graph. We want to return graph with new nodes, right? So the hash map just serves as a vehicle for us to store the cloned nodes and retrieve them when we need to add those references, right? Because each node has an array of neighbors, right? So we want to store those actual references, so we need a way to get those values. Key in the map is, the key in the hash is going to be the node's value, so maybe we need a way that, all right, so all the node values are unique for each node, so this actually helps us. There are no repeated edges and no self loops. No repeated edges. No repeated edges. A number of nodes in the graph in the range 0 to 100, right? So one thing we can say, right, to start is if the node what if we said if not node we had a similar problem the other day. What if we said if not node, right? And you can't actually return, I think, because you return the last line. We can say, what if we return nil if not node? Okay, so it seems to work. I just wanted to test something. If you say if not node, return nil, and is this the same thing? So you can do that. Yeah, I don't know why I thought you couldn't do that before, but either way, return nil if the node doesn't exist, right? Now we want to see if this hash approach makes sense. So we're visiting 1, right? Let's just say this example queue has 1 in it, right? And our hash has no values in it to start, right? We're going to pull 1 off the queue, right? We're going to pull 1 off the queue. And maybe it's important that I scaffold this as I'm right, just to see if it makes sense, right? We'll say queue equals this while queue not empty, right? Then we'll say cur equals queue dot shift, right? And it's not really a queue in Ruby, we'll just say in its array, but queue dot shift. So we take cur off, right? And then we want to visit our neighbors, right? We'll have 4 and 2. Well, the first thing we want to check, right, is if cur exists in hash, grab it, right? Otherwise, clone it. Clone it and store it. So if we clone it and store it, right? So 1 doesn't exist in our hash. It doesn't, right? So we're going to clone it, right? So we're going to say 1. Now going to be set to this clone, right, of node 1. So now we have access to this clone. And we want to say cur.val, right? Now we can clone it. And then now we're going to check our neighbors, right? And this we can iterate over our neighbors, What if we said if not discovered, right? Then we want to add to queue. So we only want to add nodes to the queue that haven't been discovered, right? We haven't discovered 4 and 2 before, right? So we want to add them to the queue. But additionally, right, we also want to do is add the edge, right? So now we want to say, hey, 1, 4, 1, 2, right? We want to do the same thing we did with cur, right? If val exists in hash, grab it, otherwise clone it and store it, right? And so we can just paste that here, right? Grab it, right? Otherwise clone it and store it. And then the thing we can do is create an edge between the current node and the neighbor, right? The clone. And then we'll say after, right? Create edge between parent and child for clone, right? Then we create an edge between 1 and 4 and 1 and 2. right, we also push them onto the map, right? And up here, right, we're also going to want to say that it's discovered now, right? So after you say, right, mark cur as discovered, then we're going to visit for, right? If cur val exists in hash, it does, right? Because we'd have 4 node 4, right? And 2 node 2. Then we're going to have it in the hash, right? But it doesn't mean we've discovered it already. That's not what the hash means. It just means that we've already cloned it, or we've created a copy of it. We still need to line up the edges, right? Now we're going to visit for, right? It already exists, so in the hash, so we're going to grab it, right? And we're going to iterate over our neighbors, right? We've already discovered 1, right? So we're not going to add it to the queue, but what we're going to do, since it already exists in the hash, we're going to grab it, and then now we're going to create an edge between 4 and 1, right? But we're going to now check 3. Since we're checking 3, we can add it to the queue, right? We're also going to create a node for it. And so I think this does make sense. So let's try and go ahead and implement it, right? So we're just going to call this BFS with hash map, right? So we're going to need hash is going to be equal to this curly braces. I think that's how you do it in Ruby. Remove this to start, and we'll change queue. We'll just say it's a queue, right? And we're going to put our node in to start. And then we can just kind of go, right, while queue dot length is not equal 0. Or maybe I think it's probably right, while queue is not empty, right? And I think you need an end. Do you need a do as well? I think you do. And then we'll say cur is equal to q.shift. And I think if we run this, it should work for now. The end we'll just put nil. We need to change our test case. So this, at the minimum, means that our while loop syntax makes sense, right? And so there's a couple axi that we need to mention, right? We need a way to mark a node as discovered, right? We don't want to use the hash map for that because we just want to. That's for cloning nodes, right, and keeping track of them. So what we could do, right, since this is an implicit graph, and an implicit graph is a graph that we pretty much know the information for as we're iterating through it. If we had an explicit graph where we knew exactly how many vertices were there, we could just create an array with n or v vertices and then just use a Boolean flag to denote whether or not we've discovered it. But since we can't do that here, since the graph is implicit, maybe we'll just use a set. I have no idea how you create a set in Ruby. Maybe it's just a hash, but there's no value. Adding a hash for a key that doesn't exist returns a hash. So maybe we'll just use the hash like it is, and instead we'll set the value to true, right? And I think you can check for the key like this. So we'll just do it like that. And then maybe we'll change hashed to cloned, right? It's just easier to tell. And then we can have something like discovered, which will be a set, right? And so we said now we want to pull cur off the queue, right? We also want to mark cur as discovered, right? How do we do that? We'll just say discovered, right? Sub cur.val equals true. right? And we say, like we wanted to say before, if cur.val exists in hash, grab it, right? So the clone, right, will be equal. The clone will be equal to the clone will be equal either to hash, oh no, it will be equal to cloned dot key, right? And we use cur.val, right? So if that is right, I guess no, actually, we don't want to do key. That's going to check if the key exists or not. We're going to say if we can resolve a clone for this value, right? The value is going to also be the node's ID, right? Then we'll get that. Otherwise, we're going to try and create a new object. Okay, and it looks like you just do human.new. So we'll say node.new, and yeah, val and neighbors. So we'll say node.new, the val is going to be cur.val, neighbors is going to be nil, right? And the initializer, it turns it into an empty array anyway. Right? Now we can store it, right? And this is where we can just say, right, if cloned dot key, right, if cloned does not have, if, right, we're storing our clones, right, if we have never stored a clone for this value or this unique ID, right, cur.val, then what we would like to do is say cloned, right, sub cur.val equals clone, right? And then we'll just say end. And I'm just going to run just to make sure that my syntax makes sense. Looks good. Now I want to iterate over our neighbors. How do you do this? I have no idea. Maybe we do something like, I'm sure you can do some iterable or enumeration type of thing. Maybe we can do something like, I have no idea. Let's check. Let's just check real quick. I'm surprised they didn't mention how the syntax for that. Oh, you can just do array.eachDo. Okay. I'll close this one because I'm getting confused. So it looks like you can just do cur.neighbors, right, dot each do, right, and we'll just say neighbor. Right, and then you have an end. So we have access to the neighbors now. And just like we said before, we pretty much want to insert the logic here, right? And hopefully our pseudocode just translates to our assumptions translate to code well, right? If not discovered, we want to add it to the queue, right? So how do we know if this neighbor has not been discovered? We have a discovered set, right? We'll check, right? If we have a key, if we don't have a key, right, for neighbor.val, right, then what we'd like to do is do we call it Q? We did call it Q. We'll say Q dot push neighbor, right? Then we'll have our end, right? And it's the other thing, right? Now we want to grab the cloned value, otherwise clone it and store it. We can just copy our code up here, right? Except we're just going to change the names, right? Instead of clone, we're going to use neighbor clone, right? And we're going to check, right? If clone subcur.val, we want to change that to neighbor.val. That doesn't exist, right? Then we want to create a new node where the value is the neighbor.value, right? If we don't have, if we've never stored a key, right, for this neighbor, we never stored a key, right, for this neighbor.val, then we want to say, right, for the key neighbor.val, set it equal to neighbor clone, right? Now I've created this clone, right? Now we want to create an edge between the parent and the child for the clone. So the way we create an edge between the parent and the child, and because of the nature of the way breadth first search works, we'll visit every edge in the case of an undirected graph twice, so you don't have to worry about deduplicating or filtering out these edges. All we should have to do is for the cloned node, right, which is called clone, we retrieved it or created it up here. We should be able to say clone.neighbors.push neighbor clone. And then what we would return, right, out of this function would actually be the node, right, the first cloned node. And since we're given access to the node, the first node is node, which is the first node we clone, right? To return that corresponding cloned node, what we return would actually be hash sub node.val. Okay. Undefined method val for integer line 94. Let me see, what if I, oh wait, I don't think it's called hash. Yeah, it's called cloned. Cloned. So our output looks like this. We have 2, 4, 1, 3, and instead of 2, 2, and 4, 4, so maybe the way we handled the simple cycles was wrong, right? We visit 1, right? We create 1, we visit 4 and 2, we create 4 and 2, then we discover 4, right? We go to that value in, we want to visit all of our nodes, right? Of neighbors of 1, we visit 4 and 2. Since we're visiting 4 and 2, let me just read this code right here to make sure it makes sense. cur.neighbors.each do neighbor. If it's not cloned, if we don't have a key for neighbor dot, what's happening is that what should be happening, right, is that we should be pushing 4 onto 1's array and 2 onto 1's array. And then when we visit 4, we should be pushing 1 onto 4's array. But instead what we have is for node 3, right, we have something happening, right? We have 2 connections to 2 and 2 connections to 4. When we visit 4, we should add 3 to 4's array. And visit 2. Yeah, I'm wondering why that's happening. Clone.neighbors.push neighbor clone. I think we can test this or figure this out with a smaller graph. Right, we'll have 3 nodes, right? And we'll just have a connection between them. Actually, we can probably test it with even smaller graph, right? We'll have a connection right to node 2, and then we'll have a connection to node 1. Okay, so in that case, when there's just 2 nodes connected to each other, we're fine. What if we had a 3rd node, right, that has a connection to both 1 and 2? Oops. We're saying our graph is not connected. Connection to 2, right? Here's a connection to 1. We have a 3rd node that has a connection to both 1 and 2. That graph would be connected. Okay. It says the graph is undirected. Graph is not connected. That is strange. This would be a connected graph, right? Oh, I guess in the way I'm defining it. Okay, I think in the way I'm defining it, the graph, I guess the way I'm thinking about it, this is a connected graph, but the way they expect input might not be this way. So what they're expecting is something like this, where 1 would be connected to 3, 2 is connected to 1, but 2 is also connected to 3. Oh no, God! I meant this. This should be 2. Wait, for the first node, we should be connected to 2 and 3. The second node should be connected to 1 and 3, and the 3rd node should be connected to 1 and 2. Right, this makes sense. I'm seeing now, right, it seems to be that this 4th node, if we imagine a line between here and here, seems to be causing an issue with the cloning. Right, so if we start at 1, right, and we follow our algorithm through, right, a queue won't be empty, right, we take off 1, we've never seen it before, so we clone it, right, then we visit our neighbors. We have never seen 4 and 2 before, so we clone them. Right, and then what we do is we do 1 dot clone, the cloned, right, clone dot neighbors dot push neighbor clone. So we push 4 and 2 on, which makes sense. We do have 2 and 3, right? Then we visit 4, or we visit 2 basically, which we imagine this is 2. I should just use the iPad. We visit 4 or 2 here, and then we pretty much, right, say, have we discovered 2 before? We haven't, right? But it does exist. We don't have to clone it, right? And then we visit 1 and 3, right? We've discovered 2 already, so we don't have to push onto the queue, right? We've already cloned 1, and we've never seen 2 before, so we do clone. Well, before we do that, right, we look at 1, right, and we push 1 onto 2's array. We can see that here. Then we visit 3, we clone it, and then we push 3 onto our array here, which is fine. Then we visit 3, right, which we haven't discovered before. We already have it. It's already been cloned, right? Then we visit our neighbors, which are both 1 and 4. I think I'm seeing the problem here. We end up parsing the tree twice precisely because since we're starting with our queue, having the node within it already, we need to actually set, right? How would you set this value, literal value in the hash? Oh, it's with arrows, right? That's because presumably if a value, to add a value to the queue, right, it must not have been discovered before. We let ourselves start with the node to start, but we never say that it's already been discovered, which it has. Oh no, wait. You do say discovered subcur.val equals true. So it should have stopped it already. But either way, we're visiting the neighbors, maybe not. Okay, so we're visiting the neighbors of 3, right? We've already discovered 1, so we're not going to push it onto the queue. We've already seen it, so we're not going to clone it. We're just going to grab it. Right, and then we're going to say clone.neighbors.push neighbor clone. I think the best thing to do, we'll just say puts queue. We do puts queue at the end, right? We'll be able to see what our queue is looking like. Okay. Something more for the values. Maybe we'll do something like queue each instead of puts, we'll do print node.val plus a space and string can't be coerced into an integer. I think there's a toS function. And then to node, we'll just put a new line. So to start, we seem to have 2 and 3. Then we have 3. I see, we're basically visiting 3 multiple times. So maybe we could do something where like we only, oh, I think I know what we want here. I think we want a distinction between discovery and processing, right? Because we end up visiting 3, even though we've already processed all of its neighbors. But we don't want to use discovery because, right, once we've gotten to this node, right, we've already discovered 3. Wait, maybe that's... We don't want to use discovery. I think we'd like to use processing. Maybe we'll say if a node, right, processed, right, the distinction between discovery is that discovery is the first time we're finding a node, right? We're processing, we're going to say, okay, now we're going to visit all the neighbors of this node, right? Processed, right, is after we visit all the neighbors for a node, now it is processed. All right, so we can delete what we have here. We can say processed, right, sub cur.val equals true. And the thing is, right, we don't want to deal with nodes that have already been processed. So this distinction allows us to have a little bit more fine tuning, right? We'll say if processed dot key cur.val, if it doesn't have, if we haven't processed this node, then we would like to. And then I think this is what we're looking for. Oh man, feels strong, man. Ruby is 2 flames. Ruby is 2 flames. Ruby is 2 flames. And actually, this is not a reflection of Ruby. This is actually the ADM. When I tried to solve this problem another time, it just didn't make sense because I was using the scene set. But the scene set is really more about discovery, and we want more fine tuning. We want a distinction between discovery, processing, and dealing with edges. And yeah, the ADM is just 2 flames, man. The ADM is too strong. ADM is too strong. I think this version of the algorithm should run in linear time, right? Where n is defined as the sum of the vertices and the edges. Edges because we're going to visit all our neighbors, so we're going to be visiting edges. Oh man, feel strong, man. That is a feel strong, man. I'm sure there's a much simpler and more elegant solution, but either way, that's a feel strong. The BFS, right? We also have O of n space, which is a good thing to mention. I'm wondering how they're drawing a distinction here. For no neighbor, if not visited, right? So interestingly enough, they find a way to make this work without that distinction. I wonder how that is possible, right? They do the same thing we do here, right? Visited is discovery. If we haven't seen the node yet, right, then we... I'm also realizing I forgot to mention, right, that this key is not really a queue. We should stop doing this. We're just gonna say array, right? Push and shift. This is not gonna be as fast as we'd like it to be. How are they avoiding this? We say visited.get n neighbors.add visited.get neighbor. That's what we had as well. But for some reason, we needed the distinction between... Is it what we said earlier? Right? The reason we needed this distinction is because we didn't add the node at the front. Right? Let's see. If we comment out this line, comment out this line. So we're back to our original problem. Is our problem fixed if we add our initial node, right, to discovered? To discovered, right, subnode.val equals true. No, it doesn't really change anything. But what they also did, this is strange to me. They add the node, they put the node on to visited, right, which is actually a map, which is no different than what we're doing here. Instead of, I think the main difference is that they do visited.put and they say visited.get, and which is the same as clone.neighbors.push. I don't quite understand what the distinction is. This is strange. This is strange. Yeah, optimizations, right? They didn't really use discovery versus process. However, this is how it works in my head. The other thing that's important to note is that we're not using a queue, we're using an array. And I always say that we're using a queue, and we're not, we're just using an array. So yeah, I would say that was a good turnout, good outcome. So we shall return tomorrow.